Welcome to our show, folks. Today, we're diving into a fascinating topic that's sure to blow your mind. We're going to explore how scientists figured out the weight of our planet Earth. Can you believe it? I mean, how do you even begin to weigh something as massive as our planet? Let's welcome our guest expert who's going to enlighten us on this incredible journey of discovery. Welcome to the show.
Thank you so much for having me. I'm excited to share this amazing story with you and your audience.
Great to have you here. So let's start at the beginning. I've heard there's a famous story about an apple and a brilliant scientist. Can you tell us more about that?
Absolutely. This story revolves around one of the greatest scientists in history, Sir Isaac Newton. Legend has it that over 300 years ago, Newton was sitting under an apple tree when a ripe apple fell and hit him on the head.
Ouch, that must have hurt. But I guess it led to something incredible, right?
You're absolutely right. While most people might have just rubbed their head and eaten the apple, Newton's curious mind started working. He asked himself, why did the apple fall down? Why didn't it fly up into the sky or float in the air?
Wow, I never thought about it that way. I mean, things just fall, right? That's normal, isn't it?
Exactly. Back then, people didn't question these things. They considered falling objects to be perfectly normal. But Newton's greatness as a scientist stemmed from his curiosity about even the most ordinary events.
So what did Newton figure out from this apple incident?
Well, Newton realized that the Earth must be attracting the apple, causing it to fall. But his thinking didn't stop there. He reasoned that if Earth could attract an apple, it could also attract a stone thrown into the air or a person jumping up. Newton concluded that everything on Earth is attracted to it by a force we now call gravity.
That's mind-blowing. So, Newton basically discovered gravity from a falling apple? But wait, if Earth attracts everything, why don't we see apples attracting stones or people being pulled towards passing cars?
That's a great question. Some people might compare Earth to a giant magnet attracting everything around it like iron filings, while smaller objects don't attract each other. While this analogy isn't entirely accurate, it's a good starting point for understanding the concept of gravity.
Interesting. So is Earth's gravity exactly like a magnet then?
Not quite. There are important differences between Earth's gravity and a magnet's attraction. Magnets can both attract and repel, while Earth only pulls things towards it. We've never seen Earth push anything into the sky. Also, magnets are selective, only attracting certain metals, while Earth's gravity affects everything.
Fascinating. So what did Newton conclude from all this?
Newton concluded that Earth's gravitational force was fundamentally different from a magnet's attraction. He proposed the concept of universal gravitation, suggesting that all objects exert a gravitational pull on each other. This means that not only does Earth attract apples and stones, but apples and stones also attract each other, and even our bodies exert a tiny gravitational force.
Wait, what? You're telling me that I'm exerting a gravitational force right now. Why can't I feel it?
That's another excellent question. Newton would explain that while all objects attract each other, the strength of this attraction varies greatly. Earth's gravitational pull is enormous due to its massive size, while the attraction between smaller objects like apples or stones is so tiny that we can't perceive it.
I see. So, coming back to our main question, how can we measure Earth's weight? I mean, it's not like we can put it on a giant scale, right?
You're absolutely right. We can't put Earth on a scale, but we can use what we know about gravity to figure it out. Since we now understand that Earth's weight is related to its gravitational force, we could theoretically determine Earth's weight by measuring its gravitational pull.
That sounds logical, but I'm guessing it's not that simple, is it?
You're spot on. Before we could even attempt to measure Earth's weight, we needed to prove that Newton's ideas about gravity were correct.
Wait a minute. You mean we needed to prove Newton's theory? But it sounds so logical.
I understand your surprise, but in science we can't accept ideas as true without evidence, no matter how reasonable they seem. Even if a person is famous and their ideas sound logical, we need proof.
That makes sense. So how did they go about proving Newton's theory?
Well, Newton himself provided the evidence. He reasoned that if Earth has gravity, then the Moon, Sun, and other planets must have it too. these celestial bodies would attract each other and orbit around one another. If Newton's theory was correct, scientists should be able to use his calculations to predict eclipses and planetary positions.
And did it work?
It did. When they tested this, they found that Newton's predictions were indeed accurate. This confirmation allowed scientists to confidently use Newton's theory to calculate Earth's weight.
That's amazing. So once they proved the theory, how did they actually measure Earth's weight?
Well, they considered a couple of methods. One idea was to place an apple next to a 1-ton rock and measure the attraction between them. Then remove the rock and measure Earth's attraction to the apple. By comparing these two forces, we could determine how much heavier Earth is than the rock.
That sounds clever. Did it work?
Unfortunately, it didn't. The gravitational attraction between the apple and the rock was too small to measure, much like how we can't feel the weight of dust falling on our skin.
Oh, I see. So what did they try next?
They came up with a second method using something much larger than a rock, a mountain. They theorized that if an apple falls straight down when there's nothing nearby, it should fall slightly towards a massive mountain if one is close enough.
A mountain? That's thinking big. How did that work out?
Well, over 200 years ago, a scientist named Hutton attempted this method. The idea was to compare the gravitational pull of a large mountain to that of Earth. However, determining the mass of a mountain was still incredibly challenging. As a result, while Hutton did calculate Earth's weight, his figure was significantly different from the accurate value we know today.
So if these methods didn't work, how did we finally figure out Earth's weight?
The breakthrough came from another famous scientist named Cavendish. He used a special instrument that could measure the gravitational attraction between two relatively light objects.
Wow, that sounds complex. Can you explain how Cavendish's experiment worked?
Of course. Cavendish's experimental equipment was quite ingenious. It consisted of 2 large lead balls that could be slowly moved closer to 2 smaller balls. At a certain point, due to gravity, the large balls would attract the smaller ones, causing them to move closer.
But wouldn't that movement be too small to measure?
Exactly. That's why Cavendish's setup was so clever. He placed a mirror in the middle of the rod connecting the 2 small balls and shone a light beam onto this mirror. As the gravitational attraction caused the rod to rotate slightly, the mirror rotated with it. Although the rotation angle was tiny, the reflected light beam could show a much larger deviation.
That's brilliant. So what did Cavendish discover?
With this precise instrument, Cavendish was able to measure the precise value of universal gravitation. This allowed humans to accurately determine Earth's weight for the first time. The value was found to be approximately 60 trillion tons.
60 trillion tons. I can't even wrap my head around that number. What an incredible journey of discovery. From Newton's falling apple to Cavendish's ingenious experiment, it's amazing how much we've learned about our planet.
Absolutely. This experiment showed us that everything, including Earth, has gravitational attraction. All objects can attract each other, and the strength of this attraction varies. Understanding what factors influence the strength of gravitational attraction is a fascinating aspect of physics that continues to intrigue scientists and students alike.
Well, I have to say, this has been an absolutely mind-blowing conversation. Who knew that a falling apple could lead to such an incredible scientific journey? Thank you so much for sharing this fascinating story with us today.
It's been my pleasure. I'm glad I could share this amazing journey of scientific discovery with you and your audience. It just goes to show how curiosity and persistence can lead to groundbreaking discoveries about our world.
Indeed it does. And on that note, we'll wrap up today's show. Thank you all for tuning in, and remember, keep questioning, keep wondering, because you never know where it might lead.